Yeah, okay. So should I start? Hello. Like, Evans, should we start? Okay. Raghav, can you hear me?
Yes, sir.
Okay, okay. Please start at 6:10. Okay, okay. We will start at 6:10 as requested. Fine, fine, fine. Ten to the power 14 hertz. So shall we start? Dipta,
Yes,
yeah.
sir, you can start.
Okay, okay. I'm audible, right, to everyone?
Yes, sir.
Okay. So good evening, everyone. So today what we will do, we will revise few of the concepts and also discuss the assignment and your queries regarding the assignment. And okay, so let's start with the first uh, Mr. Raghav's queries. Okay, so let me share the screen. Okay. Okay, we are able to see, right? So there was doubt in, I believe, question 1, right? Question 1 of assignment 9, if I say so, if I remember correctly. Okay, so the correct answer is 1000 Kelvin. Okay, the question was like, find the effective noise temperature if given the NF of around 3 dB with sky temperature or ambient temperature, say T sky, or ambient temperature as around 500 Kelvin. Okay, so by relation, what you can say that T of receiver is equals to 500 into NF linear minus 1. Okay, so 3 dB becomes around 2, so it will be 500. Now there was once I said that if you have a very low noise figure, approximately NF, which is less than 5, okay, less than 5, then what you can do, you can, instead of having a linear quantity, you can directly put the noise figure value there. Okay, between 5 to say noise figure around 1.5. This is the range where you can directly use noise figure, means directly use noise figure values, because if you do the conversion 10 to the power of NF by 10, it will come around near about the same value. For means if you are trying to calculate the effective noise temperature, total noise temperature, okay, not the only receiver temperature. So this will be 2 minus 1, which is 500 Kelvin. Now if you want to find effective noise temperature, so pardon, T effective, which will be 500 plus your whatever the noise temperature from antenna you will get. Means like there will be here in the question said the radio telescope receiver. Okay, so from radio telescope you will get around 500 Kelvin, whatever the temperature there it is. So 1000 Kelvin is your effective noise temperature. Okay, now if you replace, instead of linear using 3 dB directly, then you will get T effective directly around 1000 Kelvin. Okay, now the range was given around between 490 to 500, which was, I think, a mistake. We are already corrected it. Now, after this, also the second question was, as if the radio telescope given in question 1 has a means observing a source of 2 arc second. Okay, 2 arc second. Then, pardon me. Then find the it is this it is given that find the total antenna temperature. Okay, what will be the total antenna temperature in that case? Now what happens, this is the concept you need to get, that say you have a field of view, this is antenna here, this is your antenna. Okay, so this has field of view like this. Okay, this much field of view, and your source is only this much, and the rest of the part is what your the rest of the part is your sky. Correct? Are you getting it? Now this source will will increase the temperature of the antenna more than the sky. Means like the standard, what is the formula that you have studied is what? Delta antenna is equals to omega source by omega antenna into T of source. Okay, temperature of source. Now, what this means delta change in means the incremental change in the antenna temperature. Okay, if you are not looking at the source, you are already looking at the sky, which has 500 Kelvin as from the first question. Okay, so which already has 500 Kelvin of temperature. Okay, so if source is not in the picture, the antenna temperature will be same as the whatever the sky temperature is, 500 Kelvin. But if source comes into the picture, then that means above that background noise, it will add on to some temperature. So that temperature can be calculated as this, and that roughly you can calculate by having the square of the their sizes. Okay, means say source is 2 arcsecond, so 2 square divided by, and the your antenna is 10 arcsecond square. But this is not the proper approximation. I will get to that also. So into so this will be a kind of expression. So this will be around 200 Kelvin. So here now the 200 Kelvin is the incremental temperature here. Okay, but you have the background sky as 500 Kelvin. So total antenna temperature what you will get is 500 plus 200, which is equal to 700 Kelvin. Understood? Any questions on this?
Sir, I had a doubt in the first part, sir.
Yeah, sure. Go ahead.
So, shall I paste my procedure in the chat box, sir?
Sure.
Yes, sir.
Yeah. Okay. So, which one? Dipanshu. So NF is this. Uh, 2. Okay. Uh, where did you get the gain from? Huh?
1 second, sir.
See, there's a problem here is that uh, what if you have an antenna, okay? So
Yes, sir.
in these things, there is you shouldn't stick to whatever there is in the question. Okay, there is not, we didn't mention anything about cosmic wave, cosmic background, right? And
Yes,
cosmic
sir.
background, whatever you have saying, the cosmic background is around 2.7 Kelvin. That is correct, but if you take an antenna, see to the sky, you can't see cosmic background because there is lots of foreground. And that foreground is said to be T sky. Means that T sky includes that your cosmic wave background, whatever the cosmic background temperature is. Okay, so there is whole another field of study in astronomy where you have to extract that temperature out of the whatever the temperature you are getting. Okay.
Yes, sir.
Okay. Now let's I understood your doubt. So let's discuss on that. Okay. Differentiate between total and effective. Okay. 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 Correct. Okay. I will get back to you, Raghav, in a bit. Okay. The first one, the means Diptanshu, right?
Yes, sir.
Yeah. Okay. So the thing is, if you have an antenna, say you have a close box, and here you have an antenna here. Okay. And you're taking the reading. Whatever the temperature inside the box will be temperature of the antenna. Okay. This is the basic principle of antenna temperature is. Okay. Now, if
Yes,
the
sir.
antenna is looking at the sky, the temperature what it will get is will be of sky. Okay. Now, coming to the receiver temperature depends upon the environmental temperature also, and also the noise figure. Okay, I am saying ambient temperature means the environmental temperature in which receiver is kept, as well as the sky temperature. Both are same as 500 Kelvin. Okay, so then the directly the noise temperature will be noise temperature of the receiver will be what the means environmental temperature, or the temperature at which receiver is kept at. Okay, where it in here in the first question it's T sky into the noise figure in linear -1. Okay, this is the receiver temperature what you will get. Now adding to the Raghav's question. Okay, so the total temperature means when we say effective receiver temperature or the receiver temperature, both are the same words. Okay, if effective receiver temperature or receiver temperature means you are calculating only the temperature of the receiver, means the noise temperature contributed by the receiver. And when you say the total receiver, you consider the whatever the extra additive sky temperature is, which is on to the antenna. If at all the question considers that you have an antenna. Okay, so total wherever you will see the total temperature or the total effective temperature word, in that question you will see there will be a mention that you have an antenna, means or radio telescope. Okay, there will be this terminology present in that. That means you need to add it with the sky temperature, whatever given, whatever is given there. So that will become your entire temperature, what you will get at the end of it. Am I clear?
To be exact, you're saying receiver temperature or effective receiver temperature means the noise temperature contributed by the electronics present inside the receiver.
Correct.
Whereas the total receiver temperature or total receiver noise temperature means
not total receiver temperature, total effective noise temperature or total noise temperature.
Total effective noise temperature is it?
Exactly.
No, I don't get it. What you are saying? Total effective noise temperature or just total noise temperature?
Well, total noise temperature or total effective noise temperature, you can say. Both means effective is just a word if there is an efficiency term. Effective term comes when there is an efficiency term in that. Say I say means, for example, I will say there is a radio telescope working at an efficiency of 95%. So let's take an example. Okay, so this will clear your doubt. Okay, let's take a radio telescope, say, which has efficiency of your 95%. Okay, so sorry, 90%. Okay, now we say that the T sky is your say, let us take 500 Kelvin only. Okay, Now, and your NF noise figure, I will say it's 3 dB. Okay, till now it's clear. Means three quantities you have, T sky, and this is equals to T ambient also, or the temperature at which the receiver is kept at. So if I say effective receiver temperature or effective temperature, effective receiver temperature or receiver temperature. Okay, so this means whatever the efficiency term is there multiplied by the receiver temperature. This is efficiency of the receiver, not the antenna efficiency. This is antenna efficiency. Okay. Okay. Now there is no efficiency of the receiver is given. So every electronics terms has an efficiency term involved with it. Okay. So we will consider this as 1. So this will become your what? T ambient into NF linear minus 1, which is coming out to be 500 Kelvin. Okay, because this is 2, this is equals to 2. Okay, correct. Now, if I say total effective temperature or total temperature, so first I will say total temperature. Okay, so total temperature is the idealistic case where I will just add the T sky to it, which will become 1000 Kelvin. Okay, because we have antenna working with 100% efficiency. If I say effective term only comes if there is eta into picture, or if there is no eta, then you have to take the efficiency as 1. So what will happen? Effective temperature will be, this efficiency is also multiplied by that. Okay, so whatever temperature you have, that will be 1000 Kelvin, that will be reduced. Say it will come around, I believe so, 950 Kelvin around. Okay, so if there is not if there is an efficiency term involved, you have to take that. So effective noise temperature is means receiver temperature plus your sky temperature, and if there at all there is an efficiency term. Okay, and same goes for receiver temperature. Are you am I clear? Kind of. Raghav?
I understand what you're trying to say, but can I ask a question with reference to week 4 assignment also? Because in week 4 assignment,
I know. There was a typo. With that's why I told that calculate the total noise temperature. So there I wanted the total noise temperature there. Okay. Okay, I understood your question looking at this. So total noise temperature means receiver temperature is difference is this, to be clear. Okay, means
okay. So since this in week 4 assignment, we are using that approximation. We are directly estimating the total noise temperature.
Correct.
Instead of using noise figure, instead of linearizing the noise figure.
Correct.
And adding it with the sky temperature.
Correct.
Okay.
Correct. This means this play happens only in specific ranges of noise figure. Say if you have NF of 6 dB, then this approximation won't be valid. Okay. So there are specific noise figure values for which this approximation holds. So that means that will come after, means if you involve much more into the instrumentation part, then you will get to know that means get a hint of that, those kind of approximation, where to apply and where not to apply. Okay. So however, just follow this procedure, means like total temperature is sky plus your receiver. Okay, receiver temperature is linearize it and then subtracted with by 1 and multiply with by means the ambient temperature or the temperature at which the receiver is kept at. Okay, this is the thing. So to kind of summarize it, so T receiver is equals to your T ambient noise figure in linear minus 1, okay, and T total, okay, is equals to T receiver plus your T sky. Okay. Okay, got it?
Okay, sir.
Okay. Now the question 2. You got this one right?
Yeah, I had got 200 Kelvin, so I added it with this 1000 Kelvin and gave it as 2200 Kelvin as the answers.
Yeah. So it's here it is asking that what will be the antenna temperature, not the total temperature. Okay, even if the total temperature is asked in the
No, I gave 1200 for question 3. For question 2, I gave it as 200 because in question 3 they are asking for the total thing.
Correct. Question 3, there is a mistake in that. So it will be means it will be 1200 only. Means say 700 Kelvin is this, so 1200 Kelvin only. How? How? So question 3 is like, say now the total temperature what you will get. So you what we have 500 Kelvin sky, T sky as 500 Kelvin, correct? Okay. T receiver we got as 500 Kelvin again, correct? And delta T and we have 200 Kelvin, correct?
Yes, sir.
Now what I said, that the total temperature in the previous one I said is equals to T receiver plus T sky. Now here this T sky is coming from where? Antenna. Okay, I mentioned that whenever we are talking about T total in the question, it will be mentioned that it is coming. There is a telescope, radio telescope, or some type of antenna is present. Okay, fine. So this is coming from antenna. Now what is happening? You are looking at the source instead of means there is a sky also, but you are pointing towards the source of 2 arcsecond, which has 5000 Kelvin temperature. So T ant is the incremental temperature in the antenna is 200 Kelvin. So that means your this T sky or the temperature contributed by the antenna, this will become T sky, the sky temperature, sorry, T sky plus delta T ant. Okay, so this will be 500 Kelvin plus 500 Kelvin plus 200 Kelvin. Okay, so around 1200 Kelvin. So is that clear? Any doubt?
Yeah, I got the answer wrong, but in the end I gave the correct answer because yeah, for the first question I gave it as 1200. So 1000 Kelvin. So I added 200, which I obtained with the second question and got the correct answer. But the second question answer is wrong. It's 700.
Correct. So keep this in mind. There little bit here and there. It's a new course, so means it will take time. Okay, so it has lots of interdisciplinary stuff. So the common mistake happens. Okay, don't be bothered about it so much. Okay, but understand the concept and move on with that. Now the other thing was the other question was what? Yeah, 10th, correct. So there the wavelength is given 6 centimeter, which is not in terahertz. Okay, so you can apply the Rayleigh-Jeans approximation there.
So, but the wavelength, we are not given any wavelength. We are only given 3.33 into 10 power 14 hertz in the question.
Uh-huh.
Yes, sir. We are not given wavelength of 6 centimeter. Here it's mentioned an infrared sensor is aimed at the burner and the radiation at a frequency of 3.33 10 power 14 hertz emanating from the burner is determined to have an intensity of
Okay.
1.446 10 power minus 24 ergs per second per hertz per centimeter square per steradian. It's not,
Okay.
wavelength is not given then.
Okay. Yeah, means
Can I share my screen to show it to you?
yeah, I got it. Means like the answer with me is like jumbled up. So 3.33 into 10 to the power 14 hertz, right? Electric
Yes.
stove burner, right?
Yes, sir.
Okay. So I was thinking about what is the brightness temperature of the source. The following question. Okay, let's see this. So estimate the temperature of. Yeah. So what is the problem there here?
I used Planck's function and I got 239.399.
39.399. Okay. Okay. So which constant did you use?
H
H in which unit?
6.626 into 10 power minus 34.
Okay.
Why it's a mistake? Is it a mistake?
There shouldn't be, but I will see what is the problem here, because since the means when I was setting this question, so the unit was in CGS, right? So I took the constants as in CGS unit only. So I got around 33.7, sorry, 337 Kelvin around. So I will check once again with my calculations. Okay.
Yeah, I'll also check my calculations again and mail it to you.
Excuse me, sir.
Yeah, sure. Yeah.
Sir, actually, I did that problem and I got answer around 337.78 Kelvin.
I also got that. That.
Okay, sir.
Okay.
I'll check my calculations and I'll mail you, sir.
Okay. Sure. So
Excuse me, sir.
Yeah.
Sir, I think there that power was supposed to be 10 to the power minus 30 because we have to take in terms of centimeter. I mean the value of H, sir. So it's supposed to be 6.626 into 10 to the power minus 30, not 34.
Oh, okay.
So that's why I think Raghav might have gone wrong there.
Yeah, that might be possible. But still, if he's following MKS also, no, temperature is still in Kelvin. Okay.
Okay, sir.
If he is using if he has converted the intensity into MKS units, then the answer will come 3378 only, with 337.78 Kelvin only. Okay. So if that is correct, then the following thing will be correct. So this is means all the doubts in assignment 9 is sorted, right? With this.
Sir, question 11, sir.
Question 11, can you quote the question?
Sir, estimate the total flux of electromagnetic radiation emitted by the stove burner.
You can directly use the Stephen's Boltzmann's law, right?
Yeah, sir, I did that, sir, but the range here is way too short to include 337 and 338 there, sir.
So
the range has to be slightly larger, sir.
Wait. So same thing. What you took as Stephens Boltzmann law means the constant. How much
Sir, 5.67
into
10 to the power minus 5.
that is in which unit?
Sir, that was in, I think, CGS unit, sir.
CGS only, right?
Yeah, sir.
Let me let's quickly calculate this one.
Sir, my answer is varying by only 12, sir.
Okay.
So I checked, sir, I checked the range for the previous question since the given range was 337 to 338. So I substituted both the values in the formula, sir, sigma into t to the power 4. So the range has to be slightly larger, sir. That's it.
If I'm doing that calculation right now, also I'm getting 7,38,106.
Sir, I'm getting 122.
Sir, actually, I'm also getting 106. 738,106.1.
Correct. So there might be some calculation mistake. I just tried out my calculator. So it's 106. Okay.
Sir, can you please check with 337.7819?
7819.
Yes, sir. I take 4 decimal places.
7819. Okay. I will check whether means I will check with the NPTEL and increase the range of it. Okay.
Okay, sir. Thank you, sir.
Okay.
Sir, I have two questions. First is regarding the first question again. So in questions, this is a general doubt. So in questions where there is an antenna mentioned and sky temperature mentioned, and they are asking for effective noise temperature, we need to calculate the receiver temperature and then add with the sky temperature and give the total answer. And if antenna or sky temperature are not mentioned, then we need to calculate what will be the receiver temperature. Is it the general procedure?
Correct. If antenna is
sir.
not mentioned, the receiver temperature is your whatever the temperature they are asking for, or they will we will specifically mention that calculate effective receiver temperature or receiver temperature.
But but in question 1 also they are given what is the effective noise temperature of a radio telescope receiver. So they are not specifically mentioning it.
Okay. Yeah.
So is it safe to assume that if sky temperature is given, we need to add them, and if it's not given?
Yeah, no, it's not that. If there if we mention the total temperature, then we have to add that. And if I read it carefully right now, so effective noise temperature of a radio telescope receiver. So here it's specifically we have asked for receiver temperature. Sorry for that, but receiver temperature.
I don't understand.
Sorry.
I'm confused.
So I have made a lot of confusion. Sorry for that, but okay. So let us see. The question says that what is the effective noise temperature of a radio telescope receiver? Okay. I was only reading the effective noise temperature term, but of the receiver, radio telescope receiver. So here it is asked for only for receiver. Okay. So anyhow, if everybody has given the total temperature, or we can I will see what we can do with the NPTEL we can we will I will look into it. Okay, but read the question carefully. Like I have also done the mistake that if what they are mentioning, total temperature is always if you are having a radio telescope facility or antenna mentioned in the question and asking the total temperature. Okay, total temperature is always receiver temperature plus your sky temperature, because whatever the antenna is looking at is the sky, and that temperature will be your antenna temperature. Okay, so total temperature is typically your receiver temperature plus antenna temperature, but the source is not mentioned. That's why you take a sky temperature. Okay. Okay.
No, sir. What I'm asking is in questions, if they give the sky temperature and instead of mentioning total noise temperature, just mention noise temperature of the receiver, we need to calculate just the receiver temperature.
Of the receiver, then you have to calculate fully for receiver. Calculate
Not,
the noise temperature. Calculate the noise temperature. Then only you have to calculate the total.
Okay, calculate noise temperature means receiver plus ambient. Calculate of the noise temperature of the receiver means just the receiver.
Correct.
Okay, sir.
Okay. Okay. So if for something specific, we will add that specific part into it. Okay. So now everything is clear about week 9.
So in question 7, sir, the alpha is related to P as alpha is equal to P minus 1 by 2.
Correct. Question 7, right. Right. So your answer is also not correct, by the way. There was a range mistake there. So whatever the P, sorry, not P, alpha is equals to 1 minus P over your 2, right?
No, sir, it's P minus 1 by 2. It's just I mentioned the book, it's given in higher statistics by Malcolm Longham that it's P minus 1 by 2.
It's P by, wait, let me just one more time check it.
I have referred that book only.
Okay. The book I am referring is by
High energy physics by Malcolm Longham is the one I referred to, and there in page number 212.
Yeah, I saw the message. Yeah. Ground radio emission. Okay. Just wait for a minute. I will just cross check it. Yeah. So the book I am referring to is by Ronald Shell and Stanley Kutz. That is Fundamental of Radio Astronomy. So in that it's mentioned that alpha is equals to your 1 minus P. Wait, sorry, 1 minus P by 2. Okay. This is defined as that.
But how can it be different in
Oh,
two
yeah.
different books? I referred chapter 8, synchrotron radiation chapter
I
in the textbook that I am telling.
so you can go through this fundamentals of radio astronomy, the observational the astrophysics part. Okay. So in that it's mentioned that alpha is equals to 1 minus p, and the derivation is also present there. Okay, you can follow that and compare it, and equally let me know too. I am also interested, means I will also see whatever you are telling. But according to that, means according to the book I've referred, alpha is 1 minus p by 2. So you will get minus 2 alpha plus 1 is equals to p. Okay. So minus 2 into 7 is around minus 2 into minus 0.7. Okay. So it will be around 1.4 plus 1, and that will be 2.4. Okay. And I believe the range is given that much only. Correct. Huh. The range is given that much only, 2.4. Okay. So I will certainly go through your reference and see whether out of which two books you should refer, and I will send a mail for that also. Okay. So don't take tension. If I found that the one of the book is following wrong derivation, then I will certainly post it regarding that also. Okay. Anything else regarding assignment 9?
Excuse me, sir.
Sir,
Yeah.
Sir, if you find the formula to be different, so will the answer range be also change then?
Formula, see, either one of the books should be right first for that, means it can't be different for two different books.
Yes, sir.
Addition is common. I will go through it and see if which of them is has the correct procedure and derivations, and I will see that which one is correct and let you know in the discussion forum, and accordingly we will set the questions range. Okay.
Sir, because in last week there was an example session done, sir, and in that this formula was given alpha is equal to 1 minus p by 2.
Correct.
So
correct.
according to that, I got 2.4.
Correct. So
So
in assignment, like examples also, we use that formula only. So that's why I will see to it and let you know in the discussion forum. As far as I know, the formula alpha is equal to 1 minus p by 2. We also use that only when we are looking for synchrotron radiation in some data and all. But as Raghav pointed out, we will see. Okay. So,
I've also shared the link to a NASA JPL lecture notes. There in the last page, they have also given the same formula that I used. P minus 1 by 2.
okay, I will see to it. Okay. I will get back to this, and which is the correct one and which is not. Okay. Is that
Yes.
okay?
Okay, sir.
I have to look into it. See. Okay.
sir, in case if the other formula is correct, so can there be a range given which will include both answers?
No, we will scrap that question itself.
Okay, sir.
But however, what is the correct procedure and answer, we will share that. Okay. So all the doubts regarding week 9 is is there any doubts regarding that left? Anything left? Anything doubtful? So week 10 assignment, any doubts in that?
sir,
Yeah.
Excuse me, sir.
Yeah, yeah.
Yes, sir. Sir, this is actually a suggestion. It will be better if you could include the decimal places for such problems. So the answer is the range of the answer is varying according to the decimal places taken. So it will be better to such questions. Decimal number of required number of decimal places are specified.
Sure, sure. We will do that. We will do that. Okay. So, okay. Suggestion taken. We will see to that. That will be taken into consideration. Now, one thing you should be aware of means is there any doubt in question? I mean, assignment 9, 10. Any doubts? Because I want to cover up means a little bit of revision. Means as your exam is approaching, right? So, is there any doubts in assignments? Means the current means week 9 or the current week 10 assignment?
Can you say about sixth question of week 10?
Sixth question of week 10. Wait. 6. Yeah. Yeah. Sixth question of week 10, you have doubt.
Yeah.
Okay. So here the effective temperature we can calculate by
No, sixth question, sir.
okay. This is the fifth one, right? Okay. Sorry. So imagine we have a this one. Imagine we have a plan to use an array of telescope with baseline of 50 meters to 5 kilometers, right?
Yeah.
Yeah. So this okay. So in that in this question you have to use that delay formula. Okay. And delay formula, you remember? Tau. The delay formula tau is equals to what? B sine of sine theta by C. Correct?
Yes, sir.
So this you have to use there. Now this baseline B, here you always have to use B max. For this kind of problem, B max. Okay. So that is 5 kilometers. Then you will get the kind of time delay between two means two antennas which are the very high means very long distance apart. Okay. So if you want to have means if you want to detect something, say our goal here mentioned, our goal is to detect sources within a field of view that spans of 20 arc minutes. Okay. So this means you have 20 arc means you have to cover 20 arc minutes in that. Okay. That means you need to cover that much amount of angle. If that much amount of angle is moved, if a source is moving by that much amount of angle, if I say this is your two antennas, if it's say for example I'm not taking the extended source of 20 arc minutes second. One source moves by 20 arc second. Okay, here. Now this will have a different time delay on that. Correct. And that time delay that we can convert into frequency, because why I'm telling so because why I'm saying this, it is because when you are when you have electronic circuits and all, what happens here, the two antenna is getting means kind of correlated, then sampled by ADC. Okay, this is one way, means doing a time domain correlation, then converting it and storing the FFT, and this is called means XF correlator. XF correlator. Okay. XF correlator. And there is something called FX correlator. So if you remember clearly in the Python demonstration sessions, we mentioned that something called Wiener-Khinchin theorem, which means if you correlate two signal X and Y, means R of X and Y is nothing but X omega multiplied by Y conjugate of omega. Okay. So this is the Fourier transform way to represent it. So what you can do, you can Fourier transform the first signal and then multiply by its conjugate. Okay. Now these things, what you means these are the concepts. Now when you do it actually, what you do, you take, say you take 0 to 1 second of data, for example, and for this 0 to 1 second of data, you calculate FFT. Okay. Okay. Now this 0 to 1 second means this much amount of time, whatever the sampling is there, means the sampling speed is you are taking, and based on that the FFT is calculated. Suppose here you have 2000 data points, so the FFT means the Fourier transform will be of 1000 data points. Okay, so just listen to it, means it's not something to be worried about, but this happens. Now if you want to observe something in which has this kind means moving by 20 arc minutes, means that is the upper limit. Okay, means the maximum distance you want to measure is 20 arc minute. So then what means, that means that the time delay, the maximum time means the minimum time delay what you will get is of for 20 arc minute. And if you inverse it, then you will get the upper limit of the delta nu.
But they have mentioned that 20 arc minutes on each side. So what?
So twice of that. Twice of that.
So are we supposed to do it for 40 arc seconds?
Yeah. Pardon. Spans.
For 40 arc seconds, do we have to take this?
No. Spans on each side. No, 10 arc second, half of that. Sorry. Say antenna points at the bore side. Say 20 arc second on the both side. So you are pointing here. So here is also 20 arc second. Here is also 20 arc second. So half of that you have to take.
Okay. So, but they have asked for a bandwidth, so we will get to only the upper limit. Is it fine?
Yeah, upper limit is also that. In FFT, you need to be bothered about the what should be the upper limit. That will decide your sampling frequency. Okay. So it's like that. If you say means if you're designing an observatory, you are saying that okay, I want to observe this much angle of sources for a particular field of view, having a particular field of view. Now you decide. Now you will decide what is the upper bandwidth you want to check. Means what is the upper limit to your bandwidth, what you have to design the receiver for. And based on that, you will design, say that, okay, my sampling frequency will be this, such that I will, whatever the data I will get, that will be useful for me. Okay. Okay. Any other doubt in question assignment 10?
Sir, in question 7, what are we supposed to calculate, sir?
Question 7, can you read out that? In the previous, that one, right?
Yes, sir.
Okay. So you need to calculate the integration time. Okay. So besides this, any other doubt? Because I will cover this. What I have to revise that, I will cover this thing there. Okay. So any other doubt?
Sir, I have a few general doubts, sir.
Go ahead.
Sir, in week 6, we had 2 assignments, sir, 6.1 and 6.2. So will both of them be counted, or will there be a cumulative score for both?
That actually I don't know. I have asked professor and let you know. Okay.
Okay, sir. And sir, is it possible to get an extra assignment for week 11 or 12?
Extra assignment means?
Sir, like in week 6, we had 2 assignments. So some of us have a little low score in the previous ones. So if we could get one extra assignment for week 11
Not
and
for
12.
11. I will surely give it for 12.
Okay, sir.
Okay.
Yes, sir.
Week 11 is already communicated. So week 12, we will.
Okay, sir. Thank you, sir.
So
Okay.
also, this is week 11. So we still haven't received the content. So will it be postponed by 1 week? Because in week 11, we got week 10's contents. So we will receive the next week 11's content next week, means that becomes the week 12. So will it be postponed by 1 week?
I think I don't don't know properly about that. If you can drop a kind of a message or means something, I will get back to you on the discussion forum for that. Okay, because I need to have a conversation with my conversation with sir. Okay, professor. Okay.
Okay, sir. So also, can you share the sample question papers for the final exam?
Sample question papers. Yeah, sure. We will do that. We will do that. Means at the end of the week 12, we will do those things. Okay.
Okay, sir.
Okay. So any other doubts? So I can go with the revision and the important things you should be careful and keep in mind. No other doubts?
No, sir.
Okay, cool. So let us start with the electromagnetics. Okay, so in electromagnetics, what have we learned? We learned that there is something called electric field, which is caused by a charged particle, and if that charged particle is in motion, we get magnetic field. Now, if that particle itself is accelerated or means decelerated, that gives rise to electromagnetic field, which follows Maxwell's equation. Okay, correct. Now, in that, there are few things you need to be you should keep in mind. There is the flow of the energy in the magnetic field is given by something called Poynting vector, which is nothing but E cross H. Okay, and which means in a roundabout way, it is also the total power radiative. Okay, but this shows the energy flow in it. Means if you divide it by the time, whatever the amount of time you have seen the Poynting vector for, that will give you power. Okay, this is kind of energy you are getting. Okay, now the value of this is just mod of, means the amplitude you will get is mod of E dot H. Okay, or there is other way. What? 1 by eta into, I believe, mod of E square. Okay, I think this is the there's a eta factor and E square, because H is equals to sorry 1 by eta E. Okay, so eta is what? Permittivity of free space. No, sorry, not permittivity of free space. It's a kind of resistance factor of the free space, which is equals to 120 pi ohm. Okay, this is the value of that. Now, Now, if E and H are given, you can calculate easily that. Now, from this, we went towards something called antenna theory. Now, in antenna theory, what we have learned something called half power beamwidth. There is a half power beamwidth. The antenna means how we can characterize antenna. Half power beamwidth. Okay, this is also called full width half maxima, FWHM. In means in most of the radio astronomy textbooks, you will find it written FWHM, full width half maximum. That means half power beamwidth only. Now, this is there to characterize it. Then there is something called directivity. Directivity, can anybody tell me the directivity formula for your parabolic dish? Anyone? What is the formula you can use for parabolic dish antenna? Directivity formula.
Sir, is it 1.22 lambda by d?
This is for this.
Half for beamwidth, sir.
Yeah, half power beamwidth is 1.22 lambda by d.
Okay.
Directivity d. It is hint is it is proportional to the area.
The 4 pi by lambda square into area.
Correct. 4 pi. Correct? Huh?
So 4 pi by lambda square into area.
Absolutely correct. Absolutely correct. I purposefully written it that way. So it is directly proportional to the area. Okay. So this thing shows that if you increase the area, that will increase the directivity of an antenna. And G is nothing but efficiency. Also, so ECD, you might say, or this can be also written as somewhere as some people sometimes it denoted as eta multiplied by directivity. Now you can see that area is directly proportional to the D. Now, if you want to see kind of a means how that is possible, if you clearly remember something called Hertz dipole. Hertz dipole is infinitesimal dipole. Okay. Hertz dipole means infinitesimal dipole. Okay, that means your dipole length L is less than equals to 50 lambda. No, sorry, lambda by 50. Okay, this much small your dipole length is. So infinitesimal dipole is very small and it has nearly isotropic radiation. Okay, nearly isotropic radiation. Now, as you increase the length of the dipole to say lambda by 2, it has what omnidirectional radiation, but it looks like figure of 8. Correct? If you view from the side. Okay, so similarly to that, if you have a patch antenna or there's some kind of reflector antenna, if you increase the reflector size, you will gain more and more directive. For example, look at this formula. This is for parabolic dish. Okay. Or you can use it for aperture antennas also. Other aperture antennas also. It gives the means sufficiently good enough approximation for that. Okay. So if you see here, if you increase the diameter of the antenna, what will be the the resolution of the whatever the resolution you're looking at will become narrower and narrower. Okay. So these are the means these three terms are very important for you as a radio astronomer. Not And if you are going towards, if you are interested toward the radio as means astronomical instrumentation, then there is other parameters like reflection coefficient, okay, impedance of the system, impedance of the antenna, those things. Okay. Now, given then there is some problems which are there, which says that given the power pattern of say for example 10 say sec square theta, what will be the half power beamwidth? What you have to do here is you have to do nothing, but just you have to equate it. First you have to normalize this. Normalize this means divided by 10, that's it. So normalized power will be, say, I will say it as u sec square theta and equate it by half of it. So 1/2 is equals to sec square theta. Okay. So with this, you will get a value of theta. Say, for example, I will value of theta. You will get a value of theta. Say, if it is, say, somewhat around 20 degree. Let us assume I won't. It has a proper value, but I will say there is some other function, and you got 20 degree. Theta is 20 degree. But the half power beamwidth is, say, you have an antenna, and it has a radiation like this. So half power is here also, here to here. You have to measure here to here. This entire thing is half power. But you are from the equation, what you are measuring is the 1/2 of it. So you have to multiply it by 2. So this is very important. You have to multiply it by 2 whenever you are going calculating half power beamwidth or full width half maxima using the power pattern. Given power pattern, you have to whatever the theta value you get, you have to multiply it by 2 to get the actual half power beamwidth. Okay. Okay. Any doubt till here?
Sir, can you please explain that equating secant square theta with half, sir?
Okay, so half power beamwidth means where the power is reduced by half. Okay, let me sorry for that. Yeah, so you have a beamwidth. Okay, I will sorry for the horrible drawing, but okay. So you have a like beamwidth like this. Okay, you have a beamwidth. Okay, so in this, what you have, you can define. Say you are saying this at this portion, this is power 1, and here the power becomes half. So this thing, this angle is your half power beamwidth. Okay.
Yes, sir.
Okay. Now, and besides this, there is one more thing which is called this. This say theta, and this is phi. Phi is first null beamwidth because there is a null here. Okay. Means the power goes to 0, almost 0 here. So this is first null beamwidth. Okay. Now the equating to half comes from here. Say you have a normalized pattern here. This is normalized pattern. Okay. This is normalized pattern here. Here the maximum power is 1 and the minimum and the half power is half. Okay. So if you have a normalized pattern, then you can equate it with the half. Sec square has a kind of infinity value. I get it. So, but whatever the normalized power you have to equate with half. Okay.
Sir, half of the normalized power, sir?
Correct. Half of the normalized power. Say whatever power you have, power you have given x. Okay. So what you have to do, you have to calculate the p hat kind of thing. So which will be x by kind of mod of x. Okay. And then this you have to equate with half.
Okay, sir. Thank you, sir.
Okay. Any other doubt?
So in general, so we should not perform minus infinity to plus infinity that equate to one, like that type of normalization.
Pardon? Come again.
No, so we should aren't we supposed to integrate this function p from minus infinity to plus infinity and then equate it to one to normalize it?
Yeah, you can. That is the general way to do it. But there is lots of approximation for that. Say, what is the normalization you mean? What is the normalization?
In
Normalization?
general, it will be a root of amplitude.
In general, when you talk about normalization, it is max normalization. Whatever the quantity is divided by the maximum value that function can attain.
Okay. No, I thought it is root of amplitude like that.
No. So when we talk about normalization here, so the maximum from the maximum max norm. Okay. So you have to do maximum normalization from the maximum value the function can attain. You have to normalize with that. So that means the maximum value that function can attain is 1. Okay. So that means to be more clear, p say equals to f of x. Okay. So then the normalized p norm will be is equals to f of x by f of x max. This is what normalization means. Power normalization means for this. Okay. So and then whatever is there, equate with half. Now, if you are equating with half, that means you are finding the only this angle, but you need both sides. So that's why we multiply it by 2. Okay. Got it?
Okay, sir.
Okay. Okay.
And if we are asked for half null beamwidth, then we need to equate it to 0. Is it correct?
Correct. Equate with 0. And mostly you will find that instead of equating with 0, if you do the twice of half power beamwidth, that will result in full means first null beamwidth. It's kind of approximation that say equate with 0. That is the standard way, and the approximation is first null beamwidth FNBW is equals to twice of half power beamwidth. This is an approximation for that. Okay.
Okay, sir.
This is an approximation, but given the power pattern, it's suggested that you equate with 0 so that you will get the correct answer for that. Okay. Yeah. So any other question regarding this? No. Okay. So let us move to then after this, what we did. Just hold on for a minute. I will add new slides to it.
So this is an unrelated question. I received a mail that there's another live session tomorrow from 7 p.m. to 8 p.m. Is it true?
Yeah, there is.
From 7 p.m. to 8 p.m., sir?
Yeah, there is.
Okay.
So, yeah, about antenna, we move to receivers. Okay, there's signals and system concept. Okay, sorry, signals and system concept and Fourier transform also. Okay, so the Fourier transform is kind of makes the I would means boast and say that it makes the backbone of radio astronomy. Okay, the Fourier transform. If you understand the Fourier transform completely, you will get to know about radio astronomy, because it means radio astronomy flat means like Van-Cittert-Zernike theorem is 2D Fourier transformation. Okay, so you need to create an understanding if you want to pursue this, and for any other kind of analysis also. You need to understand that there is two sides of a coin for that matters. So there is a time domain signal for and for the time domain signal, there is the other side is called frequency domain. Okay, so that is related by Fourier transform. Okay, where there is orthogonal basis function e to the power a complex means a complex basis function which is orthogonal. So it is related by that. Okay, so which says that if you have anything in time domain which is represented as the set of means values in frequency domain, and this is very important as a representation. Okay, this means if you apply Fourier transform to your general Young's double slit experiment, what you will find that whatever the means, say you have a Young's double slit experiment here. Okay, so you have a source and you have two slits, and here is a screen. Here you will find kind of a means bright and dark fringe, correct? Hello, audible, right?
Yes, sir.
Yeah. So you will get a bright and dark fringe, and you will find that forms a sine wave kind of structure. Okay. Now, if you Fourier transform this, what you will get? You will get two impulses. Okay, and two impulses from the center. And if you see the distance, this will be around the same distance of this. Okay, so this is very important means concept that you will there is a lot of constants involved here, means that there is proportionality constant, but you will find these are related to each other. This became the kind of a backbone for radio astronomy. Say for example, you have two antenna, you can see a sky, whatever source is traveling in sinusoidal pattern. If you have three antenna, say for example, here you have two antenna, you will get kind of this much line projected on the sky. And if you have three antenna, then this will also project a line on the sky, means kind of create a gridding. And this also create a gridding like this. Okay, so you will have a gridded structure in the sky, and and the bright and the low means bright and the dark part will kind of act as a pixel, and you get an image. This is a very crude way to say. Okay, so this is how much the Fourier transform is important. Okay, so this is why we need to understand Fourier transform in the basic manner. Okay, so there are
Sir, I have a doubt here. Here, this intensity pattern that we get, which is a sine wave pattern, is it time domain or frequency domain? I'm confused
this is
about
space domain.
what phase domain.
Correct. Okay, so see, only time domain you can't Fourier transform. You can Fourier transform anything. Okay, in fact, you can Fourier transform your space also. Okay, so you can.
No, I'm asking what is the meaning of these two arrow marks that we represent here. So, if this is space domain transform to what transforming to which domain here?
Achha, okay. So there is something means the XY domain has a Fourier conjugate as your UV plane. Okay, so XY generally these are the space term which transforms into UV coordinates. Okay, UV coordinates is generally an orthogonal plane to XY. Okay, it's a bit difficult to understand in the space term. That means if there is a repetition here, it shows the how much time the thing is being repeated. That's the kind of relation you get in any Fourier transform. Means if you have a time domain signal, say in the time domain, it's very easy to understand. Okay, time domain signal, there is a continuous wave. You will get the frequency of it, means how many times it is being repeated. Okay, so in a sense, you can say that the repetition is the cause and the time domain signal is an effect. Okay, say you're saying this is there. The same thing is like this. So this is the cause and how this is reflected on the intensity distribution. Okay, this is the intensity distribution. Okay, but intensity distribution along the space, how it is intensity is distributed along the space. Okay, so here it is this and that. So now that represents the kind of the actual means, how can you say that? Yeah, the orthogonal plane by which your intensity is coming. Okay, it's let me think of an example here.
Sir, can I write something in the board, which I think will help in clearing my doubt itself and for in general?
Sure.
Okay, I'll first draw two things. Is my drawing visible, sir?
Yeah, it's visible.
Sorry for my terrible drawing, but please bear with me. These two are related by Fourier transform. So what I have drawn here is actually gravitational waveforms for two binary black hole mergers. This is strain, which we can take as amplitude, and this is time. When they are about to merge, we get this peak and we get this ringtone. And when we Fourier transform this, we get this frequency image where this frequency peaks and then decreases. But here both the axes are with respect to time. So I saw this example. So how can we use this to explain this concept? So can you?
What is there? You right? What is this thing?
Strain amplitude, strain amplitude.
So this is generally what is termed as you might have heard of it, waterfall diagram. Okay, something called waterfall diagram. So this is something you see frequency for each amount of time. Okay, so can you remove this thing?
Okay, 1 minute. Did it vanish? Oh, it's clear. Okay.
Okay, so now see, that is something called, can you mute yourself for a bit? Okay, so this is something called time frequency graph. Okay, it's not that for only if you see certain amount of time there is a frequency. So you need to know every instant what frequency is coming. Okay, so for example, you are watching for 0 to 1 second of time, and then again 1 to 2 second of time. Here there is some frequency coming, and here there is some frequency coming. The one method which we all learn in elementary means in our bachelor's or master's courses, that we integrate minus infinity to plus infinity, correct? For having a Fourier transform. But there is if we integrate the entire time domain, it will only suggest say that what are the frequency present in the entirety of the time. Okay, but we won't be able to get what frequency are present at particular instant of time and another instant of time what other frequencies is present. Okay, so here I will take a bit off-sided example about means sound. Okay, now whatever I am talking is a sound wave, and that has its own frequency spectra. Okay, if I talk for say 2 minutes and you try to Fourier transform it and see, you will get what are the frequencies present in that, but you won't be able to make out means even if you do heavy audio processing analysis, you won't be able to make out at what time, what syllable, what word I spoke. Okay, for that you need to sample the time itself of and see what are the frequencies present at different chunks of times. Say for example, I have for example, this is a time domain. I have X amount of frequency till 1 second, and then I have Y amount of frequency in second till second. So what you will get if you do the entire Fourier transform, you will get something. This is a kind of chirping signal. Okay, so you will get something like I'm drawing only one side, right? You will get something like a kind of broad this pattern. Okay, means if there is some chirping and it's kind of getting different frequencies. So you will get, instead of one single sine wave, you will get multiple sine waves, and then you will get a spectrum of it. Correct? Now, in this, when you do this, you won't be able to figure out at what time what frequency came. Okay, for that, what you have to do, you have to say take a only 1 second data and do a Fourier transform. Then you will be able to see that, okay, for this amount of time X frequency is there, and then from second 1 to 2 there is Y amount of frequency is there. Okay, so this is how that graph came. Okay, so so to analyze it more, like each instant of time, what the different kind of frequency we are getting, we divide into few time chunks, and this also results in some uncertainty. If you reduce that, if you sample it in time, that means you are multiplying it by kind of a square pulse. Okay, that will create a kind of a square pulse has a spectra of what? Sync wave, right? So in that, it will induce noise in your Fourier spectrum. And to reduce that, what we do, we generally deconvolve this function, which is called also filtering function or the filter. There are different types of filters, so we defilter that to get the proper thing. But if you reduce the time domain, that means you are reducing the amount of data. That will create an uncertainty when you are finding out what frequencies are present. That is there. I thought I went a little bit deep into that, but are you able to get it, what I'm trying to say?
Yes, sir.
Okay, so
Sir, can you tell the filtering again, sir?
okay, filtering is like, say you have a big signal, you can multiply by a filter. Filter means a simple function, okay, by which you can multiply the signal and you get the resultant signal. Say for example, if I have a sine wave here, a sine wave or some wave here, and I want to filter, say want to see only this part of it, this part of the signal, what I will do, I will multiply by a, say, square function with this. Okay, now only I will get what? This amount of signal, and I will do a Fourier transform of it. Now, what in the Fourier transform, what I will get, since I have multiplied this, so that will become in Fourier transform. So f of omega and the filter, I will say this is H. Okay, so convolved with H of omega. Okay, so that means convolution means, that means in frequency domain, you will see f of omega. Say if this is a simple sine wave, then it means it has a kind of a peak. And convolved with this, that means this is a rectangular pulse, so it will have a sinc form. And if you convolve, you will again get the sinc only. Okay, you will get the sinc function only. Okay, so that means even though you have a pure sine wave in that particular moment of time, but it is showing a sinc function. That is because of the effect of this filter, what you do. And to remove this, we later in the later stage, what is being done is we deconvolve this filter from this the entire x of omega. Sorry, the entire x of omega. This is entire x of omega. We deconvolve with this from this. Deconvolution means we deconvolve the filtering effect of this from that. So there are certain filters like Gaussian filter, like Gaussian function. The Gaussian function, if you Fourier transform it, what you will get? You will get again a Gaussian function. Okay, so that means the function shape doesn't change. So it is very easy to deconvolve that from the original signal. Similarly, there is different kind of filters like Blackman-Harris is also there. Then I think there is there are different kind of filters. So I remember currently Blackman-Harris, which we use, and then Hamming filter. Hamming filter is also there. Okay, so there are different types of filters which are used to sample a signal. I mean, kind of sample a signal. Okay.
Yes, sir.
Okay, so this is a bit deep into the instrumentation part. So what we learned, that the importance of Fourier transform. Okay, then we went towards what we went. Okay, so then we went to something called receiver temperature, receiver noise temperature, all these terms. So here I will just show you few important formulas which you should remember as a point of view of astronomy. Okay, so the first is that receiver temperature is equals to T ambient, or the temperature at which receiver is kept at, NF minus 1, and this NF is in linear. Okay. Okay, this is what it is. Now, then another thing, if you have given a system, say set of amplifiers, what will be the effective temperature you will get? So for that, there is something called Ferris formula. So T is equals to T1 plus T2 by G1 plus T3 by G1, G2, and so on. Okay, so this means this is for cascading effect. Means there is a system where you have an amplifier here, and then you have another amplifier here, and say you have a resistor here. Okay, then also this is valid because the resistor has a kind of attenuation effect. So for this, the gain is 1 by G. No, so 1 by the factor P, for example. Okay, because it will create a loss. Okay, so this cascading thing is very important because this will this shows that the temperature of the first amplifier sets the temperature of the rest of them. Okay, means if this is sufficient, if this amplifier has sufficiently low noise, okay, means noise figure is very low, TR, this TR, TM, this is valid for single amplifier also. Okay, say if you have very low noise figure, then what will happen? Based on your ambient temperature, what you keep the first amplifier at, it will it will play the major role for the rest of the system. If this has very high gain, then what will happen? All the other components will have very minimal effect, and the maximum effect is contributed by the first stage itself. Okay. Okay, this is how it is. Now, similar to this, if you have an effective noise figure, you can calculate this by NF1 plus, say, NF minus 1 by G1 plus NF minus 1 by NF of 2 second, third by G1, G2, and so on. This is like this. So you can directly add the conversion factor for each amplifier, and you can get the noise figure also. This is called Phillips equation. Phillips equation also. This is also called Phillips equation. Okay. This is one of the important things you should know when you comes to systems. Now, in addition to this, there is also temperature related to the antenna. Okay. So antenna temperature is typically antenna temperature came from the fact that if you keep an antenna inside a black box, okay, and keep it at that temperature, it is found that at whatever the value you are getting here, okay, whatever the noise value you are getting here is nothing but due to the temperature of this inside black box. Okay, this was found practically also. Okay, this concept was found, this was found practically also. So based on this is the concept of antenna temperature came. So whatever you are viewing in the whatever the antenna is viewing, that will be the whatever the temperature the antenna is viewing, that will be the temperature of the antenna. And also, irrespective of the gain and your beam width of it. Means, say for example, you have a parabolic dish antenna which has a beam width of, for example, 7 arc second. Okay, 7 arc second, which is very narrow beam. But you are looking at the sky of 500 Kelvin. Okay, then your antenna temperature will be 500 Kelvin only. Okay, so because the portion of the sky it is viewing, that is the 500 Kelvin is each and every point at the sky. So you will get 500 Kelvin only, even if it's very narrow beam. Okay, now with this concept, something came that, okay, so if we are observing a source, then what happens? Say if the source covers the entire antenna, whatever the temperature of the source will be reflected into your antenna. Say you have 7 arc second of antenna size and 7 arc second of source, which has some temperature. Okay, then same temperature will be reflected on the antenna. But say if we have the source size bigger or less, what will happen then? Okay, so then the term comes the incremental change. Okay, incremental change. So del S by del antenna into del into the temperature of the source. Okay, so this is a very important formula which is valid for what? Valid for your antenna observing a source which is greater or less than your antenna's resolution. Okay, if antenna is big, whatever the temperature change you see in antenna, that will be less. If the source size is bigger, whatever the temperature change you will see, that will be kind of a bigger change. Okay, now this is very important formula which you get from the antenna. Now when you get this, then the concept comes for the total noise temperature thing. Why total noise temperature? Because whatever you are getting at the, say, any observational facility will have an antenna, then some electronics, and then the data is stored. Okay, data is dumped into a PC. Okay, now this thing, whatever is being dumped here is the total noise temperature. Okay, whatever the noise temperature is there, and the additive noise temperature of the electronics, that entire thing is dumped here. Okay, so if you have a receiver which is contributing 500 Kelvin and you have a antenna temperature of say 400 Kelvin, okay, means del change of this is 400 Kelvin and rest of it is the sky, then you have to do this like 500 Kelvin plus 400, because this is 400 Kelvin is coming from due to the source which we are observing, and in addition to the source, the rest of the antenna is watching the sky. Okay, so that's why then this is the total temperature which is being stored, and you have to remove these two things to get what is the means value of the source. So if you don't have the proper understanding, then you won't be able to do, means this is not how it is done exactly to the point, but you should have kind of understanding why some processes when you do in either in CASA or some other pipeline, why is that happening? That has some relation to the instrumentation. Okay, so this is the one of the important formula you should keep in mind. Okay, so okay, so any doubt till now?
Sir, if this antenna is kept in the desert, like Chile, that is the Atacama, there is Alma in the Atacama desert, and
Okay.
usually the temperatures there will be around 50 degree or more than 50 degrees Celsius, which is around 300, 300, some 20, 30 Kelvin. So does that also affect this?
See, this okay, for that, say even though the desert temperature is 50 degrees Celsius, okay, that will come around 300, say for around 300 Kelvin. Okay, the electronics are never kept at that temperature. If you means if you have ever heard that some of the receivers are being cryogenically cooled. Okay, have you ever heard this term?
Yes, sir.
Yeah, so that is done because this the temperature of the receiver depends upon the ambient temperature at which the receiver is at. Okay, so if you see any assignment question, the ambient temperature and the sky temperature is same. I'm always mentioning the ambient as well as the sky temperature is same. Okay, it's a standard practice to keep the receivers at a lower temperature than the whatever the temperature you are facing outside, because noise figure or the means or the noise temperature added by the receiver onto the system depends upon the temperature condition at which the receiver is kept at. Now, coming to the second point, why doesn't the antenna will get affected? Correct. The antenna won't be affected because antenna, say that temperature is because of the something called greenhouse effect. Correct, if I'm not wrong.
Greenhouse effect or direct radiation processes. Both
Yeah,
are liable.
either of them. Either of them. Direct radiation also and greenhouse effect, but that is due to sun. Okay, now if I have, say for example, if I have, this is my sky and here is sun. Okay, but my antenna's beam width is just this much. Okay, if I look at the sun, I will get the temperature whatever the sun is at. But if I'm looking at any other part of the sky, this is actually a source. Say what I've said, that a point source which has a 5,000 degree 5,000 degree Kelvin temperature. This is a bigger source which has some temperature, but rest of the sky doesn't have the same temperature. Why? Because outside atmosphere there is kind of means vacuum, and there is no means temperature due to what's it, radiative transfer, means there is no atmosphere there, so temperature cannot be what you can say. The environment temperature cannot go up. Yeah, but to some extent, when you do observation in morning and observation during night, there is slight difference in that. That is due to the environment, means the environment warming up due to the greenhouse effects. Okay, you will see that changes, but that's not means very high amount of change. What you will what you think would be. Okay, and there is always a kind of a standing rule that if you are trying to observe something during day, you should say for a far away source, you should observe if it is opposite to the sun. Okay.
Okay, but what about the greenhouse part?
Yeah, there is a change. I said now, if you observe in day, observe in night, there will be a change, but that is not that much significant change. Okay.
No, is there a methods to filter it?
Pardon?
Are there methods to filter that?
Yeah, there are certainly methods to filter it. Means that's why in CASA, what you do always do calibration. Means when you are doing an observation, at starting you do flux calibration, and in between means when you observe, then again after that you do phase calibration, and sometimes also flux calibration also. That is due to the fact that environment is the temperature in the environment is changing. Okay. And also sky is a bit means the ionosphere is also changing. There are several loss factors for which you go and calibrate your antenna again and again between the observations. Okay.
Sir, but if we keep moving the antenna again and again, what the motors generate heat, which will be included
No,
in the
no,
noise.
that antenna is not moved at that much amount of speed. Okay, so say you have a say kind of a your observation means target you want to observe here, and based on that the nearby flux and phase calibrator is chosen that the antenna has to be moved a very little amount. Okay, there is actually a catalog of flux calibrator and phase calibrator. If you go to GMRT site, you can find the their flux calibrator, and this also VLA site has the flux calibrator and those things. Okay.
Okay,
So,
but in mornings when we observe, both flux calibrator as well as the sources flux will be affected by the environment temperature, right? So you are saying that we can account for that as the standard flux. We know the standard flux, so by subtracting the standard flux from this measured flux of the flux calibrator, we can get the change due to the daytime temperature. Is it something like that?
yeah, something like that only.
Okay.
Okay.
Excuse me, sir.
Yeah.
Sir, I had read about JWST, sir, that it is kept at a temperature of -267 degrees Celsius. So does it work at a similar with the similar principle, sir?
Yeah. If there is an instrument which is kept at that temperature, that means that those instruments are required to do very sensitive temperature means very sensitive observations. Okay, so those are because of that, to reduce the noise and the and also there is another factor to it, which is the heating due to means the swaying of the electronical instrument due to the heat. What happens if you have you if you ever learned electronics, what you see that there is something called diode, right? A diode is an active device where you have kind of a, if you increase the voltage, it will kind of increase first a little bit, and after some voltage point it will increase drastically. And there is another means if you go indulge a bit deeper, that if you increase the temperature of the environment at which you are doing the test, the curve will shift towards inward. Okay, so this is T1 and this is T2. So then T2 is greater than T1. That's why that curve, I mean that the breakdown or the shoot in the current came earlier. Okay, so and these all things depends upon the vibration of the means transport of the electron, or the vibration of the electrons, you can say, or the drift velocity of the electron. Okay, there are several concepts. So just flow of electron. If you increase the temperature, what will happen? The electron will start colliding. Means if you increase the temperature at first, what will happen? It will flow much. More of the electron will flow faster and faster. But
Yes, sir.
after some point, it will start colliding with each other because there is too much of electrons. Okay, so that's why it is very essential to keep your receivers at a fixed temperature, so that this kind of means whatever the readings doesn't get affected by this kind of phenomena.
Okay, sir. And sir, I also read that, sir, that at temperatures above minus 267 degrees Celsius, even the movement of electrons is recorded as a photon being received at the receiver. So is that true, sir?
Okay. I don't know where you have heard that, but what was the temperature you quoted?
Minus 267, sir. That is the temperature at which the infrared sensor of JWST is kept at, sir.
No. The question, I didn't get your question clearly.
Sir, there was an article about the cryocooler of JWST, sir. So they said that first of all, the temperature has to be reduced so that the electrons do not move around. And then they said that if the electrons move around, even the movement of electrons sometimes gets registered as a photon being received on the receiver.
If I put it in other terms, say for example, if you don't cool it and you let the electron move around, what it will do, whatever the reading you get, you will get some noise into it, and that is random. Okay, so what happens? Say that is totally different regime. Okay, so that is optical domain. So you have a CCD, something called CCD. Okay, a charge coupled device. Photons falls into this, and because of that photoelectric effect, means free electron is generated, and which is detected as a photon falling on it. Okay, now
yes, sir.
If this is not cooled and if you let the electron move around, what will happen? It might happen that electron will get free from the bonding by itself and get into the your device and say that okay, we received the photon because of those vibration. Okay,
so got it, sir.
Okay, so that is there. So I think we covered actually 2 hours of it. So anyhow, we will again revise this. Means again take this from. I think next week I will again start it from here, and I will show to cover this only. But for the sake of the assignment, the formula for the 4th question of the assignment 10 will be like if you follow. There is a fundamentals of radio astronomy, observational as well as astrophysics. There are 2 parts of it. Follow this. This is the kind of very good book if you want to get started into the if you want to indulge into radio astronomy. So 1 by B, the B is the baseline, and 1 by omega E delta theta. Okay, where omega E is the Earth rotation, and theta is what? Your theta is what? Theta is whatever delta theta is whatever your source size which is given. Okay, or the 1/2 of the source size, or the detect means whatever the source size which is mentioned in the question. Okay, and lambda by B, the resolution of the telescope. Okay, so
Sir, what is the unit of theta, sir?
theta, that is radians. Okay, so we will discuss this in
So which question, sir? Fourth week, 10th as week assignment. Which question?
1, 2. There is one of the question which ask about integration time. That's all. Okay, so integration time is nothing but resolution of your telescope lambda by b multiplied by 1 over Earth rotation multiplied by your beam width or the angular size which is mentioned of the source.
So is this the 7th question that you're talking about?
Yeah, correct.
So here it's 2.9 and 10 power minus 3 means it is integration time of 2.9 and 10 power minus 3 seconds.
Pardon?
In here it's given as located as far as 2.9 into 10 power minus 3 seconds.
No.
2.9 to 10 power
radians.
Okay.
2.9 10 to the power minus 3 radians it's written.
Okay.
Source located as far as 2.9 into 10 to the power minus 3 radians.
So are we supposed to do this that inverse of integration time gives this the required upper limit of the bandwidth? So something like that.
No. Upper limit of bandwidth is calculated from the tau equation, right? Tau is equals to b sine of theta by your c. See, there is two questions. One asking about the upper limit of the bandwidth. Second, integration time. Okay.
Okay.
Okay. So
Sir, the question is incomplete, sir.
which one?
Question 7 is incomplete, sir.
Incomplete?
Yeah, sir. It's half of the question came, sir. The full question didn't come, sir.
Full question didn't come.
No, sir. The question that we got here is in the previous question 3, we calculated the maximum bandwidth necessary to detect sources located as far as 2.9 into 10 to the power minus 3. That's it, sir.
Okay. Let me just let me see that. Week 10, right?
Yes, sir.
Okay. That we will report and we will give the weightage 0 for that. Okay.
So 7th question is incomplete.
Yeah, 7th is incomplete. I saw that 7th is incomplete.
No,
Thanks
what was
for
the
pointing that.
actual question, sir?
So the actual question, I will just read it out to you if it's. So the actual question is in the previous question 3, we calculated the maximum bandwidth necessary to detect sources located as far as 2.9 into 10 to the power minus 3 radians from the observation phase center. Okay, when using baselines as long as 5 kilometers. If we intend to conduct this observation at the wavelength of 8 centimeters, what is the maximum integration time in seconds we can use to achieve this sensitivity? Okay, so given the say the source size from the phase center and the baseline and also your observational wavelength, we are asking about what is the maximum integration time you would require to observe such such small sources is such small sources. That is what the question is asking. This is what the actual question is. So what I will do, I will kind of give it in assignment 12 also, this kind of question with a different value set. Okay.
Or can you share the question text here so we can take a screenshot of it and we can solve it?
Actually, I can't do that because I have solved a sheet with me. Okay.
Okay, can you copy the question alone and paste in the chat?
No, actually, there are very few people who are joining in live class, but most of the people are going with offline videos. So that will be kind of not fair to them. So what I can do, I can either put it on the discussion forum or I will discuss with my professor and we will see what we can do for this question. Okay.
Okay, sir. Or again, for now, can you tell the wavelength and the other parameters that you mentioned again? Can you read the question again once more?
In the previous question 6, in the previous question 6, we calculated the maximum bandwidth necessary to detect sources as far as 2.9 into 10 to the power minus 3 radians from the observations phase center when using baseline as long as 5 kilometers. If we intend to conduct this observation at wavelength of 8 centimeter, what is the maximum integration time in seconds we can use to achieve this sensitivity?
Okay, sir.
Okay. So this is the actual question. Okay. Okay. Then I will elaborate on this integration time concept a bit more in next kind of a revision session. Okay. So don't worry about that. So I think it's time already. So let's sign off for today. We will meet tomorrow 7. Okay. Tomorrow sir will take few extra sessions and revision also, as well as some few new concepts. Okay. So be present tomorrow.
Is it 1 hour or 2 hours tomorrow?
1 hour.
Okay, sir.
Sir, will there be examples discussed for week 10, sir?
Week 10. Yeah,
Yes, sir.
Sure.
And sir, the 2 books that you mentioned, sir, can you provide a PDF for them, sir?
We will take it offline. Okay. You can ask the question in forum. I will suggest you whatever the books are there. Okay.
Okay, sir. And sir, are those books good to follow for the course itself, or is it generally for radio astronomy, sir?
It is good for course also, as well as radio astronomy also. That provides a basic flow how you should proceed for being a radio astronomer. Okay.
Okay, sir. Yes, sir.
Thank you, sir.
Thanks a lot. Thanks a lot to you also.
Thank you, sir.
Thank you, sir. Sir, are you still there, sir?